Okay, I want to talk about graphical dimensional synthesis. Two position synthesis in particular. In this case, we are trying to design a 4-bar that has rocker output. In other words, that's pure rotation. The reason why we say that is because the rocker is that link pivoted to ground that rocks back and forth. So its end is moving on a circle. So in this case, we're asked to do a rocker output, pure rotation, in which the output is two discrete angular positions of the rocker. And there's also coupler output, which we will discuss in a second. It's complex motion. Often when we build one of these or when we design it, we get a triple rocker mechanism in which the output is two positions of a line in the plane. So, two position synthesis. We can drive a double or triple rocker by the addition of a dyad, and I'll talk about that right towards the end of the presentation. Dyad is just a 2-bar chain. So if we add 2 bars to our original 4-bar, we now have a 6-bar linkage. So let's look at example 3.1. Here we asked to synthesize a rocker output with angular displacement. This is function generation. We are asked to do a 4-bar Grashof crank rocker that's going to provide 45 degrees of rocker rotation. And so the rocker is going to move back and forth, and the angle that it's going to move through is 45 degrees. It has equal time forward and back, which means the amount of time it takes to go from one position to the extreme through that 45 degrees is one time, and that time is the same to go from that 45 degrees back to 0. Okay, so the amount of time forward and back is equal. The synthesis steps are located in your textbook. So here on the screen we have a rocker in 2 positions. Here it is in black and in red. It's the same link, it's just shown at 2 different positions in time. The book often does this. They'll use black for one position in time and red for another. So when you see this, you shouldn't think of it as 2 links. You should think of it as 1 link in 2 different positions. This is the ground position 04, and notice the angle that this rocker has been drawn at is 45 degrees. So what do we do then? Well, there's a few things to note first. A lot of these choices are up to us. For example, the location of 04 is up to us. It could be anywhere on the screen. The position of the first rocker position excuse me, could be also anywhere, but the second position has to be 45 degrees displaced from the first. After that, we need to find a position for our second ground position, which is labeled O2 here. That is our choice of distance from our first ground position. Now, it's important to note that it has to be on a straight line through the ends of that rocker. So B1 through B2, and we stop at our choice of O2. Okay, so we couldn't go off in this direction or up in this direction. We must go straight across from B1 to B2, and then we stop at our choice. We could have gone further, and we could have stopped sooner. We label that point O2. So we now have a ground link, O2 to 04. That'll be our ground link. 04 to B1 will be our rocker. So that's 2 links. We need 2 more, the crank and the coupler. Well, the crank has to start at O2, and its length is going to be 1/2 the distance between B1 and B2, as shown here. So 1/2 of that distance, this distance here, is the crank. So crank goes from O2 to A1, and then the coupler will go from A1 to B1. And that will be the end of our 4-bar. That will move this rocker through 45 degrees, equal time forward and back. Here's what it looks like. Now, I'm going to, let me say this. You see the red here, it can be somewhat confusing. Looking at the black, we have the crank, the coupler, the rocker, and ground. If we want to concern ourselves with the red, the position after it is moved through 45 degrees, it would be the crank. Then the couplers overlapped at this point, goes back to here, and then here's our rocker, and again our ground. So we have both an extended and an overlapped case. Now what I want to do is I want to go to that force effect motion app and I want to show you what this linkage looks like when it's moving. Let's see here. Alrighty, I'm going to go ahead and open that up. And before we got started, I went ahead and pulled that linkage into this application just so you could see what it looks like. And I also started off by putting a little ground position here. It's represented in this application by a triangle. And here's my rocker. Notice it's too short. I'm going to extend it up to the position it should be at. So let's see here. A little bit more, just trying to get it close to the center position. It's a little bit long, so I'm going to change that to, let's see, what about 4.5? Let me see if that makes it basically where it should be. Not quite, so make it a little shorter. Still not quite where I want it. Let me see if I can grab it and get it just where I want it to be. Taking me quite a while, so I'm just going to go ahead and delete what I have here and restart. There it is. And I'm take the other side and extend it up. Not right there. Looks pretty good. And let me get my ground position back. And then we need a coupler. We're just going to go from here to about here. It's not bad. Could be a little better. Let me see if I can slide it over a little bit. That's going to have to be as good as it's going to get. And of course my crank. Now when we do this on paper, we can of course be a lot more accurate with our lengths and making sure that everything is going through the point that it's supposed to go through. But this is the final item, and I'm going to go ahead and click on each one of these to make sure these don't change when I start running it. The lengths need to stay the same as the linkage rotates. Okay, and I'll put a motor right here at O2. And let's go ahead and watch what happens when we execute. We should see B1, the link 4, it should rotate over through 45 degrees and be right on top of the red, more or less. Again, my lengths aren't perfect. You can see here on C that it's not quite in the middle, and neither is the crank position. It's not quite in the middle, but it'll be close. So let's see how it works. And see, it comes on over and it goes back. And you can see here that the time that it takes to go from B1 to B2 is equal to the amount of time it takes to go from B2 back to B1. Okay, and so that's our linkage. That's a 4-bar that moves a rocker through 45 degrees with equal time forward and back. Okay, so let's turn our attention back to the notes. Now, in this next example, example 3.2, we're going to do rocker output with complex displacement. So in other words, we're not simply moving through an angle, which is more like simple displacement. We are instead moving the rocker through position C1D1 to position C2D2. So these lines that you see here on the screen, they are actually part of the rocker. The rocker will contain the line segment C1D1, and then as it rotates, that line segment will become C2D2. So let's go ahead and see what this design looks like. So the first thing that we do is we draw a line from C1 to C2. And then we perpendicularly bisect that line. What do we mean by that? Well, it's exactly halfway between C1 and C2, the line that we're drawing here. It goes in either direction, up and down, and is perpendicular to the line C1, C2. So it's a perpendicular bisector. And notice we went in both this direction and we went in this direction. We do the same with points D1, D2. We draw a perpendicular bisector that goes in this direction and goes in this direction. Notice it's halfway between D1 and D2 and is perpendicular to the line D1, D2. Now, where these two perpendicular bisectors intersect, they do not intersect above. They happen to intersect in this application, or in this design, they intersect below. We call that intersection the rotopole, and we are going to use that position to be our rocker ground position. So here's our rocker from O4 to C1 over to D1. That's one link. This angle here never changes. You can think of it as like a welded joint. It's not an actual rotation joint at that location. And here it is at its second point in time in red from O4 to C2 to D2. So we now have a rocker, but we don't have a ground link, we don't have a coupler, and we don't have a crank. So let's go to our next slide. All right, so here's our rocker in black. Here's the rocker in its second position in red. And notice we went up to a certain point, in this case to B1, and we drew a line from B1 to B2 straight in this direction. And we stopped at our choice. Again, this is our choice. The distance from O2 from B1, B2 is our choice. We could have gone further and we could have stopped sooner. What's most important is that the distance from O4 to B1 and the distance from O4 to B2 is the same, right? Does that make sense? I mean, if the black link and the red link are the same link, just shown at different points in time, then B1 and B2 are the same point, just at different points in time. And so we chose B1 and B2 to be, looks like on this thing, it's about 2 inches from O4. But it didn't have to be that far. We could have stopped sooner, and B1 would have been like here, and B2 would have been like here, right? Or we could have gone a little bit higher. B1 could have been like in this area, and B2 would have been like in this area. But in either case, we go straight through B1, B2, and we stop at our choice, O2, and the crank, its length has got to be equal to the length between, or I'm sorry, 1/2 the length from B1 to B2. So if we were doing this on paper, we could measure B1 to B2 with a ruler, and then for our crank, we go from here and we go over 1/2 of that distance. And then we draw in our coupler, which comes back to this point, and now we're ready to rotate, right? Complex motion. So let's go back to our force effect motion app and see how that works. Okay, so here's that linkage, and again I started a little bit of it before, and I'm going to go ahead now and get it up to where it needs to be. Ooh, I'm going to actually do I wanted to do this one. I'm going to do the red one this time instead of the black, so we'll see how that works. Alrighty, so it's a little long, but we're getting pretty close there. Okay, and now let's put in our additional items. So from this position, whoops, that's not quite right. Let me try to get it as close as I can. That's not bad. And then come over here, stop at that position O2. It's a little high, and whoops, I went too far. Let's go back because we're doing the red, and so I can't go that far over. So there we are. And my crank right there, and that's my ground link. And so if you see here, we have O2 to O4, that is our ground link. E to D, that is our crank. And D to C is our coupler. Now I know the letters that appear in this application are slightly different, right? They're different than the ones on the page, right? So on the page, the ground link goes from O2 to O4. That's the ground link, O2 to O4. But in the application, it doesn't give me the ability to change the names of the joints. It's labeling O2 as E, and it's labeling O4 as A. And so let me go ahead and make sure that each one of these stays the position that we want it to be. And point 2. Oh, the last thing, I forgot to include the line C2D2. So let me go ahead and include that line. Remember, this is not a joint over here at this part. This is simply a, let's see here. Let me see. This is just like a welded piece, just turning the rocker into an L. And in this application, if I hold down B, I can do that. And so it says that that will not open. That's not going to be a joint at B. And so let's go ahead and add a motor to our O2 position and watch what happens. So you see that? So BF moves over and becomes CD. And again, equal time forward and back. See, that's the overlapped case when it's on the black, and that's the extended case when it's on the red. Okay. Now let's keep going forward. Alrighty. So in this case, we're going to do coupler output with complex displacement. So we did rocker output in the previous two cases, but now we're going to do coupler output. So the coupler is the link that's going to move between positions C1D1 and C2D2. So when we look at these segments here, C1D1, that is the coupler link, and it will become C2D2 when it moves over. We're designing another 4-bar linkage. And this time we're using moving pivots at C and D. And what do we mean by moving pivots? We simply mean they're not ground positions. So in the previous cases, C1 and D1 were fixed. They were not places where there was motion, right? But in this case, they are the ends of the coupler. And if you recall, the ends of the coupler connect to a crank and a rocker. So they are moving joints at C1, D1. They are revolute joints at those locations. So we start in the same way as we did previously. We go from C1 to C2 with a line, and then we draw a perpendicular bisector here. Notice it's perpendicular to line C1, C2, and it goes in both directions. And we do the same thing with D1, D2. We draw a line from D1 to D2, and then we draw a perpendicular bisector through it. It's perpendicular to segment D1, D2, and we stop at a convenient choice. In other words, O4 and O2 are our choice. They simply need to be on the perpendicular bisectors. But we're not using the rotopole. You may recall in the previous example, we went to the spot where the perpendicular bisectors intersected. In this case, we're not. We're making O4 this position on this perpendicular bisector, and we're making O2 this position right here on this perpendicular bisector. So here's link 2. Here's our coupler, and here's our rocker. And so our ground is from O2 to O4. Now notice here that it shows a curved link from D1 to O4, whereas it was straight here. That's of no consequence. You can make the link any shape. What's important is simply that it have joints at this location and that location. The fact that it's curved here or curved in a different direction or straight will not matter. Okay, and they may have just done that so they could more easily show it. It would have kind of obscured C2's position if they would have made a straight line. Okay, and so let's go ahead and see what this linkage looks like on our force effect motion app. Okay, so here's that linkage, and again, we've already started working on it. And so let me make B a little bit longer, come up to here, get a little bit longer. Come on, that's not that bad. Whoopsies, that's a little bit worse. Let me see. There. Oh gosh. Oh well, like I said, it's not the best, but I think I know something I can do to make it better. I'm going to delete that, and I'm going to take this. I'm going to put it right there. There's all kinds of tricks to these things. And I'm going to extend it down to here. And that's much closer to be where I want to be. And then I have a coupler that's going to go from this position over to D1, a coupler position, and from C down here to O4. Okay, and that's a ground. Okay, and so here's my linkage. Let me go ahead and set these not to change. Alrighty. Now, this is not a Grashof linkage, so if I put a motor on it, it's going to do all kinds of crazy things when it gets past the point. So I'm going to use my finger just to show you how it moves, and just to show you that it does indeed see D1 does become D2. And so if I grab that and whoops, grab it and move it, you can see that there we go. So my D1 position did become D2, and my C1 position became C2. And of course, we can move it back. Right? Going back so we can go both ways. Now, the interesting thing about this motion is that it can go past this point. Like it can go down here, right? And that's not where we want it to go. And it can also go further back in this direction. We really want to keep it within the extreme. So in other words, we don't want it to go any further left than C1 and any further right than C2. That's what we would prefer. And so now I'm going to talk to you about how to go about doing that. Okay, so we're going to add a driver dyad to constrain the linkage between the extremes that we just saw. The extremes were C1 and C2, or you could think of the extremes as D1 and D2. Sometimes it is desirable to add a constant input motor to drive the linkage between two extreme positions. So think of it like this, like a windshield wiper on your car. It goes back and forth, right, between two extremes. But the motor that does that just turns continuously in one direction. It doesn't stop and then reverse in many cases. So we want to make it possible for the 4 bars that we create to be bounded between two extremes and also to be able to have a continuous input location for a motor. This can be accomplished by adding a driver dyad, which is 2 links. Okay. The process is similar to adding a coupler and crank as shown in example 3.1. So here's the linkage we just created, right? And we're going to add a driver dyad to constrain its motion and allow for continuous input at 06. And so what do we do to do that? Well, we need to find 2 extreme positions. So here's the rocker, is as far left as we would like it to go, shown in black here. And here's the rocker as far as we want it to go in the red position to C2. Those are the 2 extremes. Now, only thing we need to do is pick a position from O2 up, however far we want to go. And so we chose this position, so it looks like about 1.5 inches. And then here from O2 to B2, the same distance, about 1.5 inches. Okay, so again, this position on this link is the same position on the red, just at a different point in time. So now we have B1 and B2. Did we have to pick these points? No. We could have picked a point further up, like let's say right here on top of this 2. We could have picked that position as B1, and in which case B2 would have been somewhere right around in here. A little bit higher, right about right here, right? So we just have to find the same position on the 2 extremes of that linkage. Now, somebody might wonder, could we have done the same on link 4? Yes, we could have. We could have picked a point on link 4, let's say halfway between O4 and D1, and we could have picked the same point halfway between O4 and D2. Okay, and then we proceed straight, right? So once we have the B1, B2, we proceed in a straight line as far as we want. Remember, this is up to us. This distance is up to us. And where we stop, we label it 06. Because remember, we already had O2 as one ground position, 04, and our next one is 06. So how long is our crank? We know it starts at 06, but its length is equal to 1/2 the distance from B1 to B2. So we have B1 to B2 here. 1/2 of that distance is the length of our crank. And then here's our coupler, overlapped in this case, back to B1. Now, this allows continuous motion here by a motor, and it bounds the linkage from never moving further left than is shown and never moving further right than C2. And let me go ahead and share that on our Force Effect Motion app. Alrighty, so again, we've already started, and we want to go ahead and do some more building this linkage. Let's go ahead and move that, get it right where I want it to be. Ooh, that's almost perfect. Wait, there we go. And then we'll take the other end and move it down to here. There we go. Okay. So in a way, I'm doing the same thing I just did to build the previous one. There we go. We'll put it right there. And then we come down to 04. That right there. Make that a ground position. And now we're going to add our dropper dyad. So there's a 4-bar right there. But when we add this additional stuff, we will have a 6-bar. And this is kind of more of a triangular link that they created here. So I'm going to go ahead and do the same, make it kind of a triangle so I can connect it at the right location. And to here. Okay. Make that a triangle there. And let's see, this part here is welded. And there we go. And I think this part here is also welded. Okay. So those are not moving joints at E. And let's come over. See, it needs to be a little bit longer. Oh, that's almost perfect. Okay, so let's set that to be that length. And let's rotate it up. Whoopsies. Let me see something. Let me just set that there and move this up. I'm trying to get a good feel. I mean, it's, let me see. What can I do here? I'm overlapped. Let's see, go here to here. No, not gonna work. It's kind of hard to do an overlap that wants to connect. So what I will do is, I think I'm going to draw in the red instead, and that might be a little bit easier for me. So, no, let's see. Maybe I draw in this guy. Right there, and that's how far it should be, and how long should it be. Looks like about point, looks like almost 1, so I'm just gonna make it 1, and then this one should come over and be about to here. H, come on H. 6.2 is what it is. So since it's causing me some difficulty here, I'm going to go ahead and just draw a 6.2 inch long link. And then I'm going to connect it to the end of that crank. Everything's, you see how that was changing? Some of these are changing length, so I need to set these so they will not change length. That little star there that you guys see, when I do that little asterisk, means that the lengths won't change. Okay, and so now I'm going to put that on here. And let's go ahead and add a motor. And let's watch and see if this thing bounds between those two extreme positions as we desired. Okay, so it goes over a little far. I was a little bit off on some of my angles. And you see that it's kind of not going much past D2, and it's not going past D1. So D1 is as far as it goes to the left, and D2 as far as it goes to the right. Any errors are related to the fact that some of my lines aren't exactly on top of the lines that they should be in. And but you see what's cool about this is at a continuous input, We bound our linkage between two extremes, C1 and C2, or D1 and D2, so we can use a continuous motor and get that forward and back motion that we desired, even in this case from a non-Grashof linkage. So we have a 6-bar in this case. And that's all that I have for you. Thank you for watching.